Welcome everyone to the second lecture in our winter school on ethology, individual to collective identification and discovery. My name is Danny. I'm a faculty in the applied mechanics and biomedical engineering. I'm a colleague of Professor Ganga, who gave the first lecture yesterday. My lab is called Coffee Lab. That's how we pronounce it. It's short for collective phenomena. So the name suggests I study collective dynamics. I study groups of individuals, groups of organisms, groups of particles, and how interactions at the level of the agents or entities can lead to interesting group level behavior at the level of the collective. These are kind of questions I study. And typically, I come at it from my expertise, which is a modeling background. So I like to ask this question: how do you model these systems? How do you model interactions? How do you model um, the entire multi-scale process, all the way from the agents to the collective? And off late, I've also been looking at inverse problems where you ask, okay, given data, can I understand how they are how a group of agents are interacting, or what is the nonlinear dynamics given the data that you can collect? Because if you remember from yesterday's lecture, the way it ended was on the note of how ethology is quantitative. With all the tools that are out there, you can now extract useful information given a video data, for example. And then once you have that data, how do you make sense out of it? How can you extract the nonlinear dynamics and so on? Are fascinating questions in the field, and maybe we'll touch some of them in tomorrow's lecture. All right, so let's get started. I hope you're all able to see my um, slide. So I'm also part of the Complex Systems and Dynamics Center, which is a center where there are faculty from different departments who are part of it. We are interested in the broad area of complex systems and many questions of network science and data science that's around that. All right, so with that short introduction, let's get into today's thing. So I thought I'll start with first showing some videos that I've taken in IIT Madras. So this is a view from my previous house I used to stay in. I was in the 6th floor, and the building that you're seeing there right in the video is where I'm sitting right now. So that's the NAC, called the NAC building. Now it's called KCB. So what you're going to see is a very common sight at IIT Madras, and I'm sure you see this in your proximity, in your vicinity as well. So the group of pigeons that are flocking together. You see this all the time here. In fact, pigeons are such a nuisance most of the time, but this is definitely a visual treat many times. And when you're on a good top floor, you get to see this beautiful display. So actually here they are doing rather lazy rotation around the building. So I'm only showing you one movement, and it's just looping around, but they keep rotating around the building as they flock together. Some interesting things that I've also seen in the stadium, when they're all on the ground pecking, they are rather, you could assume that their movements are completely uncorrelated. There's one guy pecking going in one direction, another guy pecking in another direction, but they are always on the alert, either a true reason or a false alarm, which is most of the time a false alarm. One guy starts to fly, the neighbors who see that also start to fly. If enough start to fly, then the entire group within no time is flocking like the way you see. They go round and round, and then again after some time they realize there's nothing attacking them, so they settle down and start pecking once again. But interestingly, you also see the other case. One guy goes up, maybe another one, but not more than that. Others have not seen these guys go up. So this process does not cascade, and it dies out, and then they settle down and nobody flocks. So all this fascinating behavior you will see once you start observing. And there's one example from our own campus. Here's another example. Our campus is also known to have a lot of deers um, on the streets. In fact, deers visit our homes. They're very comfortable around humans. And this is a particular case where they are grazing as a group, as a herd, and they are trying to cross the road. What is interesting is, I'm not sure if you are hearing it, there's a strong voice of a bird that's coming in. The minute that sound comes in, comes out, one of the guys starts to look, and many others around him start to look around and so on. So you would have heard of this theory called the many eyes theory. So when you are part of a flock, you're much more protected than when you are alone, because there's a higher chance that you could spot a predator who could essentially cause you harm. So those kind of aspects you see and so on. So this is just some interesting things that are right around the corner that I thought it's interesting to start with. So these are all soft examples of collective behaviors. You have a group of animals, and then they are behaving as a group. They're interacting with each other. They seem to stay together. They seem to move in a common direction, and these are all collective phenomena or properties that are emerging from interactions between these agents. All right. So what I thought I'll do to basically start this talk and make it sorry, a broad introduction is talk about three papers. I mean, I've just cherry picked these papers and I've read them at different points in my time or in research, and I thought, oh, fascinating things that came in particular instances of time. So one is a paper from the 80s. It is the famous Reynolds model. You would have come across this. Reynolds is actually a computer scientist who wrote down a bunch of rules to simulate or animate the movement of flocks. Around the same time, there was also a Japanese author, Aoki, who came up with a model that was published in a not so known journal, but later on it was found, and then they call it the Aoki Reynolds model and so on, or Aoki Couzin model. So they give him credit as well. But the model is very simple. Every agent wants to stay away from other agents that are very close by. So there's a sort of a repulsion. It tries to align with its neighbors. It all wants to go to the same place, and it all wants to stay together as well. So these three things, when you code together, you start to simulate behavior that looks like flocking behavior. In fact, it was fascinating to see that these ideas were taken and implemented for movies in the 80s. So this is a movie called Breaking, a small movie called Breaking the Ice by Stanley and Stella. So if you look at it, there are two flocks actually. So one uh, modeling fish movement, which is basically using these models along with some more things to complicate it a little more. And there's another flock in the air that they simulate, and it's an imagined story of a relationship between a bird and a fish, something of that sort, and they break the ice to meet. So that's the story. But the interesting part was how there was interest from animation to simulate these things, so that you kind of get a realistic movement of how these guys move around. So this is an interesting paper that came in the 80s. Then in the 90s came a very interesting model. So anyone who enter collective behavior or collective dynamics will always come across this word called Vichek. Thomas Vichek is a researcher who came up with this model which is now famously called the Vichek model. It was published in PRL in 1994, or I think around 95 it got published, I think. So it talks about a very simple model. It says this theta here is the direction in which an agent is moving or a particle is moving. All right, that direction changes at every time instant. So theta at t is different from theta at t plus 1 and so on. Now, how does it change? Theta at t plus 1 is going to be the average theta within a circular radius r plus some noise. So what does that look like? So let's quickly see if we can draw it. So let's say you have some guy here, and this is, let's say, theta of t. So this guy looks at all the other guys within a radius r. So let's say this was the guy, right? So this radius is r, this r. Okay, the small r, but you can imagine smaller. Now what happens is there are guys everywhere, and it extends to infinity, right? So now this guy only interacts with the local neighborhood. It looks at all the guys who are within this, takes their average direction, and then there's a small noise here added along with it. Okay, so this was what is the model that was written down by Vichek back in the 90s. And what's interesting is that this simple one rule, unlike the three rules in the Reynolds model, here there's just one rule, can produce a fascinating behavior. It can show global order. It could show local order where small cohesive flocks move around, and it could show disorder. So all these different things were possible. So what really excited physicists was the fact that flocking was now seen as a phase transition. So from disorder, this order emerges. See, when you talk about collective behavior, we've been using this word emergence, right? So some kind of property is emerging at the level of the group. And physicists started to look at it as phase transitions. So what the plot that I've put here is the key plot that shows why it is a phase transition. On in the x-axis is the strength of the noise. In the y-axis is how well ordered they are as together as a group. Now, if it takes the value 1, it means they are all moving in the same direction. 0 is all are moving in all directions that they cancel out. Okay. So now when you increase eta, that is this noise, the strength of this particular noise, you see that there's a transition from order to disorder. So this was an exciting feature that Vichek model captures, and and this forms the bedrock for many studies in active matter and so on. And a lot of you will even see that the agent-based model I'm going to demo today as notions that are taken from this particular type of model. All right. But if you really think about the Reynolds model and the Vichek model and ask this question, okay, it is showing me collective phenomena, but is it actually capturing collective behavior? So if you ask that question, you will realize that it is not. So they are modeled, inspired from biological phenomena, but they're not actually modeling a biological phenomena. So if you really look at all the models and how they are changing as we move in time, you will realize that collective behavior models now are more about trying to explain what you observe. So continuing from yesterday's talk, I mean, ethology has become quantitative. So when you can take such data out of real animals and so on, how do you build models that capture these phenomena in the most realistic of settings? So one of the work that as people started to move towards explaining collective behavior was where they found out that the neighborhood an agent interacts with is actually topological, not metric. I'll explain what that means. So if you look back at the Vichek model, remember I drew a circle around the agent to say it interacts with everything within that circle. Now that's a metric way of looking at it. The metric is distance r, right? But what was observed in data was something very spectacular. So if this book that I put here, In a Flight of Starlings, is a book written by Giorgio Parisi, who's one of the authors of this paper that I'm going to show. He's the winner of the Nobel Prize in 2021 or 20, I'm not sure, for his work which involved in complex systems. So he talks about how they did this experiment in the 90s and failed. But after 10 years in 2000s, when they started doing this experiment, they had better technology, better optics, better cameras, and so on, that they were able to do what they set out to do in the 90s. So what did they set out to do? So in Italy, in a particular place, they have these starlings, just like how these pigeons that I showed, right, in the beginning. These are starling flocks, and they are known to flock in huge numbers, okay, in thousands or even more. Um, so this is a particular snapshot of starlings that are moving. So they keep these cameras in different positions to capture the 3D motion of these birds. And then once they capture, they try to look at their spatial organization and so on, characterize many things, and then ask the question, how are they interacting with each other? And they found something very spectacular. So this is a very interesting plot from the paper. I hope you'll go back to check this paper out and what these anisotropy factor and other things mean. But what they found out was a bird on an average interacts with 7 closest birds. So there's a very fascinating thing, right? Initially, the idea or the thinking in the field was, okay, let's draw a circle. That's the physics way of looking at it. There's a field, which means let's draw a metric distance and let interactions happen between everything in that metric distance. But from there, we moved on to looking at topological neighborhood, where you now talk about interactions between agents but in select numbers. And this also makes sense from an ethology viewpoint. So given that the cognitive load that these animals can take is limited, if you really think about it, packing many birds within a metric distance is going to be of no use for them. They cannot take in so much of information. So on an average, all that they process is information from 7 neighboring birds. All right, so fascinating thing. So the field has been evolving like this. So once you take real data and ask these questions, you start to see these really fascinating results. And this is one of the pivotal papers that made a shift in the kind of models that we started to develop for collective behavior, which had topological neighborhood and so on. Okay, so these are the 3 papers that I wanted to show you to basically give you a broad intro to how this field is evolving and how fascinating it is. So modern research in collective behavior is all about explaining observations because we are able to make observations. But for students who are beginning in this field, what do you really think is required? I believe that I tell my students, you need to develop an intuition to understand emergence of collective phenomena. So given a set of interactions, you need to be able to think of how these interactions are going to play out in a system. So to really do that, you need to do two things at least. One is start by simulating simple behavioral models that are already there, not with the aim of using that model to explaining a behavior, but as an aim to study these systems, to study emergence, to study how agent-based models can be put together and so on. And you also need to be able to characterize the collective behavior from observation. So how do you make meaningful sense from data? So these are 2 broad things I think are very essential, and that's why I've planned to do the first one in today's lecture. I've taken the Couzin model, and we are going to go through the model. I've written codes also. I will take you through my codes and show you how a typical agent-based model code can be written. So if you've not attempted to do that previously, this is a good place to start, and you'll get a feel for how that is done. And hopefully tomorrow we'll look at how to interpret data from these models, from real observations and so on. All right, so let's talk some behavior in a couple of examples. So I was very excited to read all your entries when you guys wrote about this. Some of them were spot on. You got the point very nicely. Some of your observations were not right and they were skewed because I had given you a very little data, right? So if you've seen the extended videos, you would have realized that was not the case. Some observation, only very few were wrong. So I was very happy to see that you're all making the right observations. So I thought, okay, let me put that back here and write a bunch of things that you. So what do you see? What behavioral aspects do you see? So these are experiments done in my collaborator's lab in Center for Ecological Sciences in IIT, Professor Vishu. All right. So one of the first things to notice, the fact that these agents are active. They are spending their own energy to move, and they're making decisions to move, and they have a particular movement strategy. So when you look at a video like this, you end up your mind automatically traces, in some sense, the group dynamics because you're looking at a group. But if you zoom into concentrating and looking at one guy, it's actually a sped up video, you will realize it shows a lot of interesting behavior. It stops and moves, and it stops, it turns quickly, and all of those things you will start to see. So also very important details to notice. They make quick turns and so on. Then as a group, you will start to see a lot of interesting things. One is the fact that they have a common direction. We call this polarization in this literature. And what you'll also see is that there is no specific direction that is preferred. So for example, let's say if there was a chemotactic field here and they were responding to it, That's like an external field that is constraining their movement. So you'll expect movement to be about that field's direction. But here, they turn in all directions. They are not bound to go in either clockwise or anti-clockwise. They can go in all any direction, any way possible. And there are different times at which they turn. So some turns are quick, some turns take their own time, and so on. So there's a huge distribution in how these things are done, and there are collective turns. So sometimes you will see that some agents go to the side, but they don't necessarily result in a turn, but sometimes these turns do happen. So there's some kind of a cascading effect of decision making that's happening inside, because at the end of the day, there is no brain for the collective, right? There are these individuals and they are making decisions, and only when the decision cascades to the entire group, the collective ends up doing what ends up doing something significant, and then you realize that as a decision of the collective. But actually there was no, I mean, you have to decouple your mind from thinking about the collective's decision. There's no decision making at the level of the collective. There's only consensus that they arrive at because of individuals making decisions. All right. So they also stay together. We call this cohesion or cohesiveness because they're staying together. And you'll also realize that there are no leaders here. So even if you were to think that the guys in the front are leading a certain direction, they change very rapidly. So there are no set leaders doing this. So you could say that the direction in which they move and the things that they're doing are all spontaneously emerging from the interactions that are happening. And there's a huge resistance to split into groups. That's part of this cohesion. The cohesion is very strong, that it's not allowing that. You'll also see that motion is in some sense punctuated. So as a group, they stop at some point, do something, and then they move, stop at a point, do something, and so on. So a lot of interesting things that are going on, and you see huge fluctuations. Any property you were to measure, let's say average near neighbor distances, average density of this group, average perimeter, whatever you were to measure, you will see that it fluctuates. Okay, and that's interesting. So there's a lot of stochasticity that you see here as well. And you see that both as individuals and also as a collective. You can keep going on making many observations because there's a lot to see in a video like this. All right. But this is a video that you saw, some part of this video is what you saw, but let me also show you a very different video and let's try to make some observations. So this is a pedestrian movement video. Here also there is decision making. There is some kind of a behavior. There's some kind of and all the agents are intelligent. And we're going to ask the same question: what behavior do you see? So this is a scene from Bombay. It's just taken from YouTube. There are three kinds of people here. Ones that want to get into the train, ones that want to get out of the train, and people who don't want to change their, current state. Either they want to stay out or stay in, whatever. So what I want you to do is just look at these agents, these people, and where they are moving, but where they want to end up moving. Okay, so I want you to track the heads of these people and see whether their movement of their heads matches their intent of where they want to go. So you'll realize that the direction and intent are very different. So actively, these agents are trying to identify how to reach the entrance or away from the entrance, but there are a lot of interactions going on around them that does not allow them to go. So in this example, the collisions dominate the overall movement in the system. So even though they want to go in a particular place, collisions stop them from moving. So let's say if there was an observer sitting on the top, measuring and tracking these heads, it won't be able to differentiate a person who's going away from the train versus a person who wants to get into the train but is pushed away, because both their movement will be in the opposite direction, but their intents were very different. So now what is really exciting is, from a behavior identification viewpoint, you have to now ask, so what data do I look at? I can't simply look at movement of just a person. I have to look at the neighborhood as well. I have to take into the fact that interactions are playing a role and they're dominating, and hence they play a role. So, given that we are talking about behavior and identification and so on, I thought this was an interesting thing to do. So these, so let's stop here for a second. So I've shown you two videos, right? One where there are a bunch of fish moving around, and you have here a bunch of people trying to do something. Both these, I would say, are agents which are interacting with each other. Each agent has a goal. Each agent has a set of rules that it's following. And whatever you see here is the net effect of all these agents interacting with each other. All right. So you could let's say I could have put another video where there were just particles, and these particles were moving because maybe they are Janus particles. For those of you who don't know, Janus particles, there are reactions that happen on the surface of these particles that may help them propel. So let's say these particles propel. They're bumping into each other. They're moving through a fluid, disturbing the fluid, and interacting with other particles long range. They will also show behavior which is of which is interesting. So even a particle that wants to move forward could bump into other particles, not be able to move, just like how you see people here wanting to move in a direction but they are bumping into other people and unable to move. So what I'm essentially trying to say is collective behavior is across a variety of fields, and you can start thinking of all of them in the framework of an agent based model. It is possible, but today we are only going to look at ethology and behavior and that context alone. All right, so let's move forward. So where do we want to get to ultimately? So let me show you some simulations of agent-based models to tell you this is where we are getting at. So when we look at a phenomenon and then try to model some aspect of it, this is what we do. So this is an example. So we are going to look at this model in great detail, but something of this sort is what we are heading towards. Where in this case, what you'll realize is if I know the velocity at every instant of time, I will be able to move these particles from where they are to where they should be in the next time instant. Okay. So all I have to do in the modeling strategy, in the simulation strategy, is figure out this velocity as a function of time at every instant of time. And how does that change? That depends on the neighborhood, the domain, and how it interacts, and all the assumptions that you take in to the system. All right. So here, each agent moves as desired. They are trying to avoid collision. They're trying to follow. They're trying to stay close. Uh, so if you see, they were all going around and around each other, right? That was not pre-programmed. That emerges from the interactions. So how does something like that emerge? Is what something we'll look at in great detail. But very quickly, let me show you another model just to show how different these models can be and we can capture different behavior. Motivated by the video that I showed you initially of people moving in opposite direction, bumping into each other in the railway station. Here is a system where there are two kinds of agents. The red agents desire to move left, the blue agents desire to move right. And what I do is solve a force balance problem. So there is a force that tells what each particle's desired direction is, and there is a force that of interaction. When two particles come in close proximity, they interact. When I put just these two and start solving these equations simultaneously, the force balance will tell me what the velocity is at every instant of time. And once I know what the velocity is, I'll be able to move these agents with time. So what you're seeing is such a simulation. So you'll see that collisions are modeled, collisions constrain the movement. There is no notion of intelligence here. Though I got inspired to write this model based on you know the the traffic problem, the pedestrian problem. The pedestrian problem actually has intelligence of agents, right? But there is no notion of intelligence. But still, if you noticed clearly, you will see that they spontaneously formed lanes. So you will see that these lanes are formed. So there was no pre-programming absolutely, but lanes were formed automatically. They break, and they reform, and so on. All right. So when you start thinking of agent-based models, how do you start thinking about its implementation? Okay, so this is where the technical part of today's lecture begins. So I think about it in three ways. Okay, one, there is an overall structure to your agent-based model. Then there are these behavioral rules. So, and then there's network topology. So to make this broader, because the lot of interest for inanimate collective behavior as well, the behavioral rules here could be replaced by the physics. It could be hydrodynamics, it could be electrostatics, whatever. All of that comes here. So the behavior or the physics, the overall structure, and the network topology. Any agent-based model that you look at it through this context. Only then you will be able to compare between agent-based models, realize when you're tuning an agent bot, what class it belongs to, and all of those things become easy to understand when you think in this context. So what do I mean by overall structure? There are many ways to think about this. Are there rules for movement? What do I mean by that? So let's say velocity at a particular instant is determined based on neighboring guy's velocity, my distance to somebody else, my distance to the wall, and so on. These are rules coming in. Once the velocity is known, you move the particle. So those are rules for movement. But at the same time, I can solve a force balance. What do I mean by that? I solve F equals ma problem to move a particle. So once all the forces are known, I will know the acceleration. From that, I can write the velocity. From there, I can move the thing. So what is the overall structure that you're using? Are you using rules for movement? Are you using a force balance? These are all things that come in the overall structure. Then there is superposition principle. So let's say there are multi-physics in your system. Are you going to add them? Are you going to implement them one at a time? How are you doing it? What the context will set all of this. So in many of the physics problems, we always add forces. Net force is always sum of all forces. So that's a very physics way of thinking. But do animals do the same thing? When you think of forces or rules in the behavioral context, how do you think about it? So superposition principle or not. Then comes the idea of synchrony and asynchrony. Many times when you write these models, you will say, okay, there's a force acting all the time, every time to all particles, they're all interacting and evolving at the same time. But behavioral context, when the fishes were moving, maybe one fish stopped moving when another fish was turning. Maybe one person did something when the other person was not making a decision. So there is asynchrony that can be part of your system, and it could be a big deal in terms of the collective behavior that comes out. So you need to keep an eye out for it. Are you looking at asynchrony, unsynchrony, and so on? Then how is noise taken care of in the system? Is it added as an afterthought, or is something fundamentally probabilistic about the way interactions happen? And then what are the states of the system? So if you were to ask, in a typical particle model, what are the states of the system? There'll be a position, there'll be a velocity. But take a behavioral thing like a fish, for example. There's a position, there's a velocity, there's a heading. And the fish typically moves in the direction in which it's heading. So there are three states, like what people see in liquid crystal kind of models as well. So what are the states of the system? And so on. And then is your domain periodic, bounded, is your thing 2D or 3D, and so on. So all of these choices come under the overall structure of your agent-based model. So that is one thing. Any literature that you read, that is some of the things that you have to look out for. Okay. Then let's move on. The next vertical that I have you look at is behavioral rules. What are the different behavioral rules of the physics of your system that dictate the dynamics that you observe? So we looked at alignment, attraction, so alignment is simple, right? So they try to align. Attraction is they want to be close to their neighbors. They could be spontaneously turning in some direction, because these are live agents that are also moving around for safety reasons, right? They're looking around and so on. They could have spontaneous motion. So you can even think of Brownian noise in that sense. So let's say there is noise, thermal noise in the system that makes it move in random directions. That's also spontaneous in some sense. There could be reaction to a wall. So let's say there's a boundary. It either wants to stay close to the boundary or it wants to move away from the boundary and so on. Then it wants to move away from other agents, which in light of predation and fleeing and foraging and so on. So all these different behavioral aspects come under the behavioral rules. So in a generic sense, hydrodynamics, multiphysics, all of those things will also come here. All right. Then comes the third category of things that you have to look out for, which is the network topology. At the end of the day, an agent is considering what all agents in its neighborhood to interact with. Is it interacting with its nearest neighbor? Is it interacting with neighbors within a metric distance? Or is it interacting with neighbors in a topological sense? Or is it randomly picking? Or is it picking neighbors that are what are called most influential and so on? So all these different ways of looking at neighbor topologies. And why this is very important is, depending on how they pick, the interaction network will also evolve in the system. So we have shown in one of our papers that, let's say, if agents pick other agents to interact with in a manner that results in a well-connected network, cohesion is guaranteed. But the minute they interact in a way where the network is broken, so this guy interacts with here, this guy interacts with there, but there's no interaction between these guys, then the network is broken and cohesion is not guaranteed. So some of the so to really understand emergence, you have to understand um, how the network topology is and how that has an impact um, on the dynamics and so on. So again, just to summarize this slide, the lot in this slide, there are three aspects that you have to look at when you're looking at agent-based models. One is the overall structure. So in the overall structure, you'll realize that the interactions, the behavior rules are not part of it. But the way it plays out is, dictated by the overall structure. And then comes the behavioral rules, where the context-specific rules come in. And then there is network topology, which tells you how interactions are playing out and what causes emergence and so on. So let's look at this one model today. So what I plan to do is basically talk about Couzin model. And just a quick thing, Couzin model came in the around the year 2002. So it's pretty old, it's 20 years old. So it's not a cutting edge model, but it's a good model to start. So a lot of interesting aspects are there. It is metric based interactions, not topological, which is what is now used in most models. But it's a good place to start to learn modeling. So this is the thing that I was talking about earlier. So just because we are progressing towards a data driven discovery of things does not mean that we completely leave these older models, because these models help build intuition for the dynamics and the emergent dynamics and so on. So hopefully this helps you in that path. So this is this model is presented in this paper that came in Journal of Theoretical Biology. So the first author is Couzin, who's a big shot now in the field. Has this army of people working in Constance in Germany. All right, so let's get into the specifics of the model. There are a lot of things that are talked about in this paper, but I'm only looking at the model. Maybe I made a little small changes to the model so that it's tractable and easy to do for us now. But otherwise, I'm only looking at the model. Okay, so even if you go to read this paper in line with this lecture, look at the model. All right. So this is just an excerpt from the thing that kind of gives a picture of the overall implementation of the model. So let me just summarize what this is saying. There are two rules that are spoken about. Rule one is agents move to make sure that there are no other agents in their immediate vicinity. So there is a zone right around them where they don't want other agents to be. So you remember the Reynolds model we talked about. These guys don't want to collide with other guys, so they move and make enough space between this thing. Then comes rule two. If rule one is satisfied, if there are no guys in the immediate vicinity, then the agents align, attract with other neighbors around them. All right, so behavioral interactions of the type alignment, attraction, and so on come into play only when there are no one in the immediate vicinity, which is priority one to move away from them. All right, so that's the overall picture. So now, what's the agent that is here? So basically, what I'm trying to show you also is, how do you look at any model in literature? how do you extract it out and look at it in detail so that you understand, all these things. So one of the things that I want to show you is what are the states that are of interest, what is being modeled. Couzin agent has a position and x, y. So I'm going to model everything in 2D, although Couzin initially posed everything for 3D. So there's an x, y showing the position. And if you also notice, there's a heading direction. There's a heading. The fish moves in the direction in which it is oriented, right? So there's a theta direction. And once you know, and basically the way the Couzin agent moves is once you know the velocity, you can move it from position xy to the new. So what will be the velocity? So it will be some speed multiplied by the cosine, cos theta and sine theta. So that's the velocity. So it is not some velocity that keeps evolving with time. It is conditioned on the theta. Theta evolves with time, and once you know theta of t, you know the heading direction, and multiplied with the speed, you know where the agent is heading. And from x, y, it will change to something else in that delta t. Okay, that's how things work. So how now what happens to this theta? Because this agent is swimming and it can turn to the left or to the right, it will turn with a rate omega. So that's what Couzin assumes, some constant rate omega, some constant speed s naught, and then it turns towards whichever side it desires based on its interaction, and then moves. All right. So let me contrast this with a different kind of model. Okay. So remember the model that I showed for the sake there were red agents and blue agents moving in either side, right? Sometime back, modeled after people in a railway station. So there I used a particle model where there is no notion of heading. There is only x and y. There is no theta. So where will it move? Whichever direction it is being pushed. So the velocity comes from a force balance, and whichever direction it is pushed, it will move. Unlike this case, where it will move only in the theta that is there. So the theta has to rotate and change based on behavioral interactions. All right, does that make sense? Okay. Now let's go back and ask how are these rules done? So Couzin, in going back, so these are the broad overall things, right? So we talked about superposition of rules and so on, right? So here there's an additional thing that comes from Couzin. He says there are these non-overlapping zones for repulsion, orientation, and attraction, and neighbors in these zones alone can have an impact. So what does this mean? Okay, so there is a zone of repulsion. So within this region, if some guy is there, that takes top priority. Rule 1 will work out. If rule 1 does not have to be done, then it will look at other agents in the zone around it, which is a non-overlapping zone, only this zone, which is called the zone of orientation. And if you notice, I've cut out a part here, right? That's the part where the agent can't see. So there's a blind zone as well. So vision is not necessarily 360. So for us, I would have cut out here, right? For these animals, it's cut out much less. They can see much more than we do. And then there's a zone around it, which is called the zone of attraction. All right. So when an agent is here, this is attracted to that. When an agent is here and it's aligned this way, this will also align in that way. When an agent is here, it will move away from that agent. All right. Does that make sense? So these are how the rules are given in this particular model. All right. So how do you go about coding such a thing? So before I show you my code, I want to help you build a mental picture of the pseudocode for this particular, or the algorithm for this particular process. So how do you do it? So the idea here is you find the desired direction of motion, which I call it as D. Okay, you are at time t, you're going to move to time t plus tau, and you need to know in which direction you want to move. So that is given by this variable D. Okay, the whole idea is to figure out what this D is. Once you know D, so you have an agent like this, right? And this is its current heading. Now let's say if you find out that this is your D, what will this fish do at this instant of time, this agent? It has to turn this direction. And the same agent, if it finds out, let's say, that this is D, what will it do? It will try to turn with a constant rate omega. All right, you got the idea. So if I find D, I am done. I know with which direction it will move, and then all I have to do is move it with the same velocity s naught, and at the turning also I do the constant turning rate omega. All right, so it's a simple procedure where all I have to do is determine D at every instant of time. So this is how you should think about it at the overall setting. If I know D, I'm done. So what is going to determine D? The interactions, the cases, the overlapping zones, all of that are going to have an impact. But once I know D, I am done. All right. So now let's go. So what is the thing that you do? Rule one, right? The agent has to make sure that there are no other agents within the zone of repulsion. Right. That's the first thing it has to do. So the if condition is if agent has neighbors within the zone of repulsion. So what does it do? It will move away from these neighbors. So how does that work out? So let's say this is the agent and this is the zone of repulsion and there is an agent here. This has to move away from it, which means, let's say this vector, I call it as Rij. This will move in the direction minus Rij. So D will be minus Rij. If there are many guys within that zone of repulsion, it will be summation of minus Rij for all the J's. Does that make sense? So it is trying to move away from all of these guys. So there's a superposition here, but overall this kicks in because there are more than one guys within that zone of interaction. All right. Then, so this is the overall structure of the code. So if there are neighbors within the zone of repulsion, this is the only thing that will happen. But when you don't have that, you go into this region where there are multiple options available. There are at least 4 things that can happen. There's case 1 where there are no neighbors at all. This one guy is a loner, far away from all the other guys. Okay, in which case D will be directly given by its instantaneous velocity. Makes sense, right? There's no one to influence him. What's the deal? He's just happy in life doing whatever he wants. Then there's case 2 where there are neighbors only in the zone of orientation. What does that mean? So there is this guy, zone of repulsion, there's no one there. Then there's zone of orientation where, let's say, some guys are there. And then there's zone of repulsion where there's no one. Okay, so it only aligns with them. So what happens? Okay, some things come, some things don't come. So when there's orientation, what happens? It aligns with them. So D will be summation over all J Bj's. Does that make sense? So V is telling you how they are oriented. In fact, it should be V divided by the magnitude. You only want the direction. So there are all these guys within the zone of orientation. They're all pointing in some direction of which they are going. This guy aligns with the net movement of the. All right. So that's what happens when there are neighbors only in the zone of orientation. Then comes neighbors that are only in the zone of attraction. Okay, the very similar thing. So there's this guy, no one here, but there are guys here. It's a very less dense system. So what does it do? It gets attracted to all of them. So maybe the centroid here. So it takes a very interesting form, very similar to this. It takes a form very similar to this, but opposite in sign. It has the Rij. overall G, but a positive sign because it moves towards them. All right. And then comes the case where there are neighbors both in, this is most likely the case in our simulations, where there are both in orientation and in attraction. In which case, what do? You find DO, which is orientation, then you find D A, which is attraction, and then you simply add them together and take the average. All right. So this is Couzin model. So when you do, there it is. When you do that, and then after you do all of this, you add some noise just to bring in the aspect that an agent is unable to make non-erroneous estimates of what it wants to do. See, at the end of the day, it's an organism trying to figure out what it wants to do. There'll be error in what it does, right? And then once you identify D, what do? Going back to how we started, you turn towards D. So if this is your angle and this is your D, you do a clockwise rotation. If this is your heading and this is your D, you do an anti-clockwise rotation. As simple as that. All right. So do you get the overall picture of what's happening? Let me quickly run you through the entire thing. So this is how you structure the code. So you look at the rules and put them in these logical statements. So if there are things within the zone of radius, you do something else, you do something else, and you expand all the cases. And after that is done, you do other embellishments like the noise that is added, and then the turning that you add. So how do you begin writing a code of this sort? You will begin writing by writing a code which will only do the first step. What is that? If you knew D, it will turn to that direction. That's how you start writing the code. And you would test that code out. You'll visualize that code. You will make sure that the D is some random thing that is turning here and there. And this fish keeps turning wherever D is. When that is done, your overall layer is done. Then what do? Put many of them together. They're all not seeing each other. You put the first if statement. If agent has something within the zone of radius, move away from it. Otherwise, just keep doing what you're doing. The minute you put that, you will realize that they are stopping to collide. And then you put in, okay, now when there are guys within the zone of orientation, you do this. When they're in the attraction, you do this and so on. So the reason why I'm talking about this is, so let's say you have 10 interactions that are going on. One of the questions that came out earlier, this is in line with one of those questions. So how do you know which one is having an impact on the dynamics that you see or the dynamics that you want to observe? To even get an intuition for these things, you have to start putting things one after the other and start to see whether they're making sense. Whatever you expect, is it happening or not? All right. So that's the reason why I've structured it this way. So you start from the outer, where once you know D, you know where it goes, and then slowly start building and putting in all the details. All right. So what you do, so one other thing that I've added, which is not part of the original Couzin model, is I've put a boundary. And the reason is very simple. I don't want these agents to wander off to infinity because they're metric interactions as well, right? Once it goes out of the zone of attraction, which is the largest, there's no way two guys will interact with each other. So I don't want them to wander off. And hence what I've done is I've put a boundary, an arena. So what I've done is this is the algorithm that we discussed, right? Algo of Couzin. I put this under another if loop, which says if an agent is within the arena, do all of this. Else, bring it back. So does that make sense? So all I'm saying is, if an agent is within the arena, do the Couzin model. Else, the first thing to do would be to reflect it back to the center. And then you add the noise, turn, and so on. All right. So that's just pictorially represented here. So what I'm going to do now is I've written the code in MATLAB. So you don't have to worry about the exact code. What the point of the code is to show what I was talking about in the previous slide as to how I've structured it. so that it gives you a head start into how to write. Okay, so if you're already comfortable with MATLAB, I will the Google Drive that Professor Ganga shared has already some contents. I will put the MATLAB code. I've also put the MATLAB code in it, so you can take a look at it. In addition to it, there's a Python code as well, which my student Bala has written, which you can take a look at if you're comfortable with Python. All right. So, but this demo right now is to show you how these codes are written in Java. All right. So this is a typical MATLAB, um, you know, scripting script file. So this is just basic stuff of I've cleared all the variables, I've cleaned it up, I've closed all the figure files and so on. So when you're doing multiple simulations, these keep accumulating, right? So this is just to make sure that's not there. Here, n is the total number of agents. Okay, if I want, yeah, okay, from the looks of you guys coming closer, I think you want me to make it even bigger. Is it better? Okay, all right. So there are a couple of things here. Don't worry about it. I've kept arranged these agents as 6 rows and 10 columns, or m rows and n columns. That's why there are 2 extra variables. But ultimately, n is the number of agents that I have. Okay, and this is the amount of simulation that I'm doing. I'm going to simulate it for 3000 time instance every zero point 0.1 seconds. So when you're, let's say if you're used to solving differential equations, this point one is like the step that you take as you figure out what your rates are and then you move. But here, in addition to being that, it has an added meaning, which we will come back to at the end. Okay, so if I move the simulation every dt time instance, leave this for now. This is the turning rate at which the agent turns, but for now I have commented it out. I don't want it to turn. I want it to take its uh, desired direction at one shot. So that's what I've done here. Okay, so this L here is the length size of the arena that I've set, and I've also marked what the tank's center is. Okay, and then this is basically me initializing the position and velocities. I've only said, okay, there are n guys, there are x and y components, and for all these time steps. So I'm just making zeros and making sure they are all initialized. And then here comes the initial configuration. So what is the initial configuration? So it could be anything. It could be some random configuration. Here I've made sure this is just a code to make sure that they are in a square grid. Okay, you don't have to worry about exactly how I implemented it. All you need to know is what it is doing. Okay, square grid, and this is to make sure it's at the center of the tank. All right, and then I give it some initial headings. It could be in any direction. This is saying it's a random number, uniform random distribution, and then this is 2 pi, so it could be in any angle that it wants. And then the velocity is cos theta times sine theta. I think I've kept the speed to 1. Okay, I've kept the speed to 1, so you don't have to worry about S naught. So S naught is 1. All right, then uh, then this is just a way to plot the boundary and so 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 let's just run this to see what we have. So if you notice already, I already started plotting stuff, right? So that is one of the things that I think is a good practice to follow when writing, doing agent-based models, because the idea is not to write a bunch of codes or ask ChatGPT for codes, but to when you're putting this and writing it together, you want to know that whatever you want is exactly what's happening there, right? So you have to keep plotting them and visualizing them at every step. So I wanted things to be ordered as a square, as a rectangle. It's ordered in the rectangular grid. It's at the center, done. There's an arena of a certain size, done. All right, but let's stop here. Do not. Ah, okay. All right, so that's the first 41 lines of the code. I've just plotted an initial configuration. That is all. Okay. Now let's move down. Now what do you do? Now comes the Yeah. So now comes the dynamic simulation. So there's something that's going to be keep changing with time. So till now, what I plotted was time instant one, right? At the zeroth time, it was there somewhere. They're all initialized. Different angles are given. They're positioned at the center. It is done. The simulation is ready to move ahead in time. Now, what do you do? So as time evolves, so this is just these are tricks. But you could what I'm doing here is this: my position is updated based on velocity. If I know the velocity, so time, I'm moving from time t equal 2 to time steps. Okay, so t minus 1 is what I know, which is 2 minus 1 is 1. That's the first one. Okay, so the position at time t is simply the previous position plus velocity times dt. Simple first order difference for the kinematic equation dx by dt equals b, right? Simple stuff. So if I know velocity, I know dt. And what is my velocity? I'm saying that my velocity, current velocity, is same as the previous velocity. So you see what I'm doing here? I'm not coding the Couzin model as yet. I'm only beginning to build the framework in which Cousin's model will slowly emerge. Okay, and then I'm doing the same visualization plot along with one extra line that makes it seem like a movie. Okay, so let's run this. So this is the initial, it pauses because I've asked it to pause. Now, the minute I press any key, it will start to go. So you'll see, right, they're all in a proper nice square lid, but uh, each guy is in a different thing, because I've said random uh, places. I mean, they can be in random orientations. All right. So now let's begin. I'm going to press a key. Do you see what's happening? They are going in exactly the same velocity, the same direction their previous direction was, with no change. There was absolutely no change. They are not seeing the boundary as yet. They are not seeing each other. So they're invisible. So they are colliding. They're moving through each other. All sorts of physically, impossible events are happening. But this is the overall framework. If you find your velocity, your agents will move. You've finished that part of it. All right. Okay. Okay. Then let me open this. Now what I can do is make it slightly better. I can say, okay, at least see the boundary. So what do I do? This is a loop where I do this for every agent independently. Okay. So within the time t equal to 2, when I move t equal to 2, for every agent, you can do this. So I'm going to uncomment these set of lines. So what is this telling? This is having a if loop. You remember our if loop from our thing, where if something is within the boundary, do the Couzin model. If it's outside the boundary, reflect it back. So this is going to check only for whether it's outside the boundary or not. So this line is the if loop that says, because the circular boundary, you just have to measure the distance from the tank center. If it's less than, if the greater than or equal to L, which means it's outside the boundary, I'm saying find my D, which is pull it back in with some error. So I've added some error so that it's, there's some variability, but pull it back in to the center. And then if it is not, then dj is simply the velocity, and velocity is dj. You got the idea? So the only feature I'm bringing in is react to the boundary. Okay, so let's do simulation now. So again, they're not seeing each other. They're just moving in the direction that they want to. But they come in. So now you know that no matter what you code, your agents will be within your arena. They will not escape off to infinity. All right. So how are they bouncing back? What model you exactly use? All those depend. So there are a lot of work by Guy Therolos and his group where they try to extract these models from data to see how they react to a boundary and so on. Here I've used some random model that's easy to code so that it just bounces back in. All right. Okay, so let's go back. Okay. Now I can add a third feature. Did you notice something that happened? The velocity or the orientation of the guy just became its desired direction. So let's say there was an agent and it figured out a desired direction. It instantly took that desired direction. There was no turning towards that thing. So now what I'm going to do is bring a turning. So this part of the code, what it does is basically tries to figure out what the turn angle is. Is it a positive angle or a negative angle? And then if it's a positive angle, it will do a positive omega. If it's a negative angle, do a negative omega. That's all. So it's just turning gently towards the direction which it wants to go to. Okay, not an instantaneous turn. Which means I also need the turn rate, which I had initially commented out. So let me go and uncomment it. And now run the simulation. So again, they're not seeing each other. They're just moving in the direction that they go. Now when they go to the wall, look at what happens. Oh, they're bouncing off again. Okay. Hopefully this should work. Ah. So the boundary does not become a hard constraint, but you start to see that they turn very gradually and nicely. They don't show rapid movement, but rather nicely. In fact, you will even notice guys who travel by the wall. They go via the wall as well. So all sorts of stuff can happen, and you start to see this behavior. So much more gradual, nice movement. All right. So you understand what I'm doing, right? I'm making the outer part, which is if I know the direction I want to go in, I will be able to go. Then make sure everything's within the boundary. Then now turns are slow and so on. So each aspect you'll have to figure out how to model, but this is how you put it together as you write an agent-based model. Okay. So so this is what I would call stage one in some sense. You've made your agents move. Now you bring in social interactions. Moving on to stage two. So the same code, but I deleted most of the lines from my original code to make it simpler. So now what I'm doing, again, same n and so on, but now I'm bringing in zone of repulsion. All right, only the zone of repulsion. I'm making them see first. Turn rate, what I'm simulating with time, tank properties, uh, my initial positions, all of these are the same velocities, and then when I do this, it'll plot the first frame. Okay, now coming in. So remember the if plot, the if condition. When things are within the boundary, outside the boundary, do something. If they are inside the boundary, then you go into an if else statement to check whether there are anyone to repel. If there's anyone to repel, you have a rule from the model, which is move away from them. Okay. So once you write that, you have a new DJ. So initially, what was the model? Initially, the model was if there are no one in the boundary, if they're not outside the boundary, just keep moving in the direction of your previous direction. But now that's not the case. If not within the arena, look now for neighbors within your zone of repulsion and react to it. So that's what you're seeing. And all the other things are the same. The turn angle is the same and so on. So shall we run this? You'll start to see that they move past each other a bit. If you notice two guys colliding, so let's say these two guys are approaching, right? Just watch this. you'll start to see that they move away from each other a little. If you want to see this a little more clearly, what you can do is we can go back and increase our turn rate to a very large value, which means it can instantaneously turn to the desired direction. Let's run this. You see that they're reacting with each other. They are starting to sense each other. The minute they are within their zone of repulsion, they turn away from them. So they are starting to see each other. So this is how you start putting in one physics at a time, one phenomena at a time to model the system. So when they do it a little more smoothly, it was a little harder to see. Now it's a little easier to see. That's the only difference. All right. So that's stage 2. So what have we done? We made sure we added an extra thing. So if they are within the boundary, then you check for repulsion. So what does repulsion require? It requires you to check the distances between these guys, right? So all that is checked here. So I look at the distances. These are functions within MATLAB, but all I do is find the distance in between every pair of agents and use that information within the loop. All right? Okay. So let's move on to the next stage, which is the full model. Now here, what do? I bring in all the things that are required. Zone of repulsion was already there in the previous one. I bring in zone of orientation, and then zone of attraction as well. These are non-overlapping. That's why you have this plus. Then there's a site I bring in. It can't see the entire 360, something lesser, so 270. Then turn rate, and then even you can add some error. I've just put it to 0 for the moment. These are all the same things as previously, and this will plot the first step. Now coming to the dynamic simulation. So once the simulation starts in the dynamic sense, you need a bunch of things now. So if you look at this, I'm finding the distances that was required even for my repulsion. Then I look at some logical arguments. So I'm trying to see, is there anything within the alignment zone? Is there anything within the attraction zone? Is there anything within your site? So what does all of this do? So let's stop this one here. Okay, I just put a random thing to stop the simulation at that point. Let's look at is align. So this alignment is basically zeros and ones matrix, okay, of the size 60 cross 60 or n cross n. So if let's say so is alignment of, let's say, 10 cross 20. It says 1, which means 10 and 20 will align. 10 will align based on 20, 20 will align based on 10. So the similar thing will be there for 20 and 10 also, because it's only a distance-based thing, right? So this is just telling you whether it will align or not, whether it's part of the vision. And I'm taking all of that into consideration. And I use this for the rest of the code. You understand that? So is repulsion tells you whether there's something within the repelling distance. So let's look at some is repulsion. So if you look at, they are non-aligning, right? So is repulsion of 20 cross 10, will it be 0 or 1? It will be 0. Because 20 cross 10 is in the alignment zone. So which means it's not part of the repulsion zone. Similarly, is attraction will be 0 because they are all non-overlapping zones. All right. So you come up with these ways to do the logical structuring, and then you go into the detail where, again, the first if loop checks whether it's in the arena. If it's in the arena, first checks whether there's a repulsion. No repulsion, then it goes into this case where there are 4 cases. Case 1, case 2, case 3, and then case 4, no interaction. Each case has the same thing. So you remember the average of alignment and attraction. Only alignment, only attraction, no change. All right. So once you do this and simulate, you have your Couzin model. So this is a case where they are aligning and they're able to move as a flock. That's the condition that I've taken. They go to the boundary, they will do a turn, and then they'll come back again and they will get polarized. And if you leave it for enough time and a larger boundary, they will even stop doing these turns that are coming in. They will be perfectly aligned into one thing. All right? There's enough disturbance now that it's resulting in this kind of all right. So let's look at another. See, already the fluctuations are reducing, but now again the boundary will induce fluctuations. All right. Let's look at another. So how do we look at another parameter? We have to go and change the parameters that will affect the dynamics. What are some of those? The zones. So let's put zone of orientation or alignment to 0. What does that even mean? It means that it does not align with any of its neighbors. It makes sure it's away from them, repulsion, and attracts to them. So let's see what we get. So what you get is these guys who are moving about a point. You've seen these bees near a light, right? So it's like a swarm. There is no order in the system. So they just move and then they just keep moving. So that's what you get. The minute you add a little bit of alignment, let's say 2.5 or so, let's see. You will start to see these patterns which we began our thing with, right? Where we wanted to get to. So these are called milling patterns. So where you would have seen these Discovery Channel videos where these huge schools of fish mill, right? This is one of those things that is captured by this model. So there is a vision that is making sure it does not see everywhere. Little bit of orientation, huge levels of attraction, it is able to form these milling patterns. So what I'm telling you is, when you have a model, this is the way in which you code. You get the outer covering first, and then you slowly add things in. If you go all in to model the entire thing, it becomes a huge mess, and it becomes very difficult to understand which effect gives rise to which, which interaction gives rise to which effect, and so on. All that becomes very hard to disentangle. This is an example of a milling. So let's go back to the presentation. We have a little more to finish. So if I ask you the question, what is, again, going back to the overall structure, multi-physics or the behavior and network topology, what is this Couzin model? So you can obviously see that there was a repulsion first, social interactions later, which was an essential aspect of the model. It was synchronous. That is, at every instant of time, you evaluated D. So now remember, I told you, when you solve a differential equation, delta T with which you solve, you can keep reducing it to make your ODEs better. But here, if I kept reducing delta T, which was 0.1 fixed here, what will happen is that it also implies that the fish interact so much faster. If instead of 0.1, I had 0.01 in this model, it is telling you that the fish interacts 10 times faster. So there was a coupling between interaction rate and also the delta T in which you're evolving the model. Then there was noise just added to the overall choice 2D. You had all these interactions, and it was a metric topology and no overlapping zones. So just to give you a feel that any model you take that is of interest for your particular context, you can start casting it in this format to understand what kind of a thing it goes into. And some aspects to keep in mind, some good practices to follow when you are writing your agent-based models is to always assemble your agent-based model piece by piece, outer structure, inner structure, one by one, and visualize at each step, which means you have to write a visualization module which is fast and quick so that you can run it and visualize it as you run these simulations to make sure whether it's right. Then always good to test specific cases where you know how your agents should behave. Let's say when there's a repulsion and two guys have to repel each other, you put them to meet head on and see what's happening. When things have to be within an arena, check whether that's happening and things of that sort, right? Then always run, because these are all. So one of the key aspects of the system is the fact that there are large degrees of freedom. If you notice, there are many agents, they're starting with many initial conditions, they're going all the over the place, right? Which means you have to run enough simulations with enough initial conditions so that you get a grasp for what it is predicting. Sometimes you will think that models, you've simulated the model, then you realize that only when you run enough that there's something wrong with it. I'll talk about one of those in the coming points. Then scan through the parameter space, vary all that as required, especially in the extremes. Let's, for example, how I put the zone of orientation to 0, which means it will not orient. If you start to see orientation, you have to question whether your code is right or something non-intuitive is happening. All right, so these kind of things are good practices to follow in general. One of the key things that I've always found important while trying to diagnose whether these, whatever you're simulating is right or not, is the symmetry argument. First of all directions are accessible. There is no special directions. It's not like there's one attractive zone in the arena or anything, which means it can go in all directions. So when you do enough simulations and plot all those trajectories together, it should span the entire 2D space. If it is only going in one direction, it means you made a mistake in the code. And typical mistakes that people make is when they take average of angles and so on. So let's say you take the average of 1 degree angle and 359. What should you get? In the sense of a vector, it should, so between these two, right, it should be 0. But if but you take a normal average, it will say 180 because of the circularity. So generally things will all go in 180 degrees, things of this sort. So you will have to make sure that you use vector all the time, not do any of this angle business and so on. So these kind of things become very clear to, because let's say even if you made that mistake and you simulate the system, it look like fish that are moving. But the only problem is all this fish will always move in 180 degrees. So only then you realize, okay, something is wrong. Okay, so symmetry argument and all of these things, and make sure constraints are always satisfied. If, for example, an intersection is not allowed between two guys, it should never happen. So these are extreme cases that you make sure things are, are always satisfied. And when you do these checks, you will make sure that your ABM is working well. All right, so there are some variants of these ABMs that are there, but I think I'll allow you, so I'll share these slides so you can look at these slides. In the interest of time, I think it's good to stop here and just talk about the assignment which will lead to the mini project for this lecture, for this winter school. So I put a PDF. So in that, Professor Ganga shared a drive folder, right? So there's a lecture 2 folder with all necessary things. There's a PDF called assignment or something of that sort, where all the details are there. And just putting it again here to explain it to you guys. So one of the fish that is called Raminos tetra, it's Semigrammus rodstromus, is known to exhibit a very interesting movement behavior. It is called burst and coast movement. Basically what it does is it will burst and move and then slow down, and then turn direction, again burst, turn direction, again burst, and move and slow down. Okay, so I want you to model this. So one fish, okay, we are only, this is an assignment for which the the solutions will be posted on Saturday morning. Okay, so you'll be able to see codes that work, but I want you to try it yourself so that it will prepare you for the mini project, which is an exciting project, which I'm keeping in suspense. So what I want you to do is one step at a time. Okay, first simulate the burst and coast with minimal details. Remember how I did this stuff, right? If I know which angle I'm going in, which for how long and so on, it will be able to go. So the details are there in the PDF. Then put them in an arena. Then bring in some randomness. I've told you how to do that. I've explained it in the PDF. And then bring in some more detail. Again, I've explained it. And then, so once you do this, you've essentially simulated burst and coast for a single guy. All right. So the solutions for this will be posted on Saturday morning, and along with the details for the mini project, which are to be submitted on 17th. All right. Any questions at this point? I'm done with what I have to tell you guys.